All right. Even though we're starting 20 minutes late, we won't end past 8:30. It should be a hopefully short lecture. So the problem you were just working on involved a bunch of cities in Germany, and you trying to find the shortest path that connects all of them. So we'll formalize this problem in like a couple of minutes. So yeah, let's just get into the information. So a bit of information regarding the remainder of the semester. So we finished our satisfiability and constraint programming saga, so we won't be giving too much attention to those anymore. They might appear here and there just to, connect things together. Like today we'll talk a little bit about CP, but otherwise we're pretty much done with that saga. So today and then the next 2 lectures, there's only 3 lectures including today, we'll be on some special topics. So today we'll talk about TSP. Next time we'll talk about a little bit more about TSP, maybe some other stuff. And then the last lecture, I'm not entirely sure yet. I think next lecture I'll give a couple of options about what you want to hear about, and then we'll go from there. So the next lecture on the 21st is going to be as normal. Again, it might start a little bit late. My train will arrive at that same 6:52 time. Today was miserable. First the train arrived late, and then we got to the station, and then the doors wouldn't open to the train, so we're all just standing there waiting for the doors to open. It was miserable. And then I ran here, which was not fun. Also at work, they didn't give me my lunch. I ordered lunch and they forgot to deliver it. So the only thing I've eaten today is a bag of chips. So kind of dying today. Okay, so next lecture, normal. We'll start a little bit late. Week of Thanksgiving, no in-person class on that Tuesday. That's just not going to happen. We'll see if I want to do some sort of not synchronous, but some sort of online thing, whether that be a live Zoom session where you guys can join or just something pre-recorded. I haven't decided that. I might poll you guys. And then on the 5th, that will be the last class. So there you'll do your final project presentations, and maybe we'll cover a little bit more content. But that's pretty much it. As far as due dates, it's just the checkpoint and then the final project.
How is the checkpoint working?
Yeah, so I think the information is outlined on the final project document. So I think you just submit a document detailing what you've done, and then we'll look over it, give you feedback. If you guys think that it would be helpful to meet with me or the TA, we can definitely do that. Just send us an email and we can, just meet with you guys, see what you've done so far, give feedback there. But yeah. Any other questions regarding project or these last few weeks? I don't know, it feels like the semester is kind of flown by, at least for me. Okay. So, yeah. We'll be talking a lot about the traveling salesman problem today, or traveling salesperson problem, abbreviated TSP. And so this problem is essentially exactly what your exercise was with Germany. And the formulation looks something like this. You're going to have a weighted complete graph. And you might say that, okay, Germany isn't really a graph, but we can formalize it as a graph in just a moment. But you have a weighted complete graph. And we want to find a tour of minimum total cost that visits every vertex exactly once and returns to the starting vertex. So as a smaller example, maybe you have 4 different cities or 4 different vertices in your graph. And for it to be directed and complete, we'll say that between every pair of vertices, there exists a pair of opposite pointing edges. So that would be one set, and we have another set like this, there, here, and then the diagonals. So this is the type of graph that we'll deal with. And in context of Germany, you can think about the vertices representing the cities, and then edges could be maybe like flights. You take a flight from Hamburg to Essen. I'm going to run out of German cities, so, that's what the formulation looks like. And each of these edges will have a weight or a cost associated with it. You can think about it as distance or, I don't know, price. So maybe from here to here you have to travel 10 miles, and we'll just say that it's symmetric. So A to B is 10 miles and B to A is 10 miles. So that's your input. Graph, complete, directed, have edge weights. Since there's symmetry along these edges, we might just represent it as an undirected graph. So, just the same thing. There. So now we're just removing the arrows for simplicity. And if we label an edge 10, that means both directions it's 10. So that's just notation. And so this problem has a lot of different applications, perhaps most obviously in routing, but also in a lot of other fields like logistics and producing microchips. And it turns out to be NP complete, hence why we're talking about it. Question?
Can you talk for a bit about producing microchips? Like, I can't figure out why it's...
Yeah, I'll post a little, reading on Ed. I came across, some article, and I briefly skimmed over it, and oh, this seems cool, but I didn't really comprehend it, but I'll post that, and we can look over it. But yeah, I guess you can think that when you're producing microchips, you have to shove a bunch of transistors into a small area, and so it's kind of a similar thing. Doing a lot of different placements in a constrained space.
And the symmetric assumption is only for simplicity, right? It doesn't change the...
Yeah. I think it can differ, but for simplicity, we'll keep it the same. Other questions on the formulation? Okay. What's on my next slide? Okay, just a bit more notation. So like I said, complete directed graphs, parallel edges. We won't deal with self loops. And then for notation, we'll use these parentheticals. I, comma, j means the directed edge from I to j. So critically, I to j is not the same edge as j to I, since we have direction. So that might be important later on just to deduce what's going on. And so a tor can be thought of as a permutation of the vertices. So a tor is going to be the path that we follow along the graph. So if I were to give these names, V1, V2, V3, V4, and anyone who has not done graph theory with me before, I do my V's a little bit weird, just to differentiate them from U, because U, V, good luck with that. So an example tor is just a permutation. Maybe we start at vertex 1, we go to vertex 4, we go to vertex 2, then vertex 3, and then we'll come back to 1. And since it's a complete graph, all of these edges exist. It's just that this will have some associated weight with it, which might differ from a different tor. There's a chance that I'll be using tor not in this exact definition where we're visiting all of the vertices. I might use the word tor just to describe a partial tor, but you'll get the point. So that's more notation. Question?
Isn't that view sufficiently different from the view in tor sufficiently different from a v?
Yes, but sometimes I don't put the little tail there. When I do graph theory, it's that and that. When I'm writing quickly, it's that and that. So I don't want to make that mistake. It's a good question. No one's ever asked me that before. Other questions related to the problem notation or handwriting? Very good. Okay. I think the next slide. Oh, I forgot to mention weight, but these edges have weight. This is weight 10. So we would say W of V1 comma V4 equals 10. That's weight. Okay, so this is an example. The graph is actually identical to this graph right here. It's just we've drawn it in the undirected sense, and it's just a reformulation of K4. They're isomorphic. So in this particular example, the optimal tor cost is 80. Just following the red lines traverses all 4 vertices. You stop where you start, and it costs you 80, which is better than anything else. So this is going to be the running example that we use pretty much throughout the lecture. So we'll just keep this in mind. Okay, so before we get into solving it, question?
Do you know the answer to, like, if you have 4 vertices specifically in your graph is complete and undirected, do you always disregard the highest edge weight one? It's
Think
yeah.
so, maybe. We'll see like a lot of different ways of solving this, and one involves computing a minimum spanning tree and then basically duplicating the graph and doing some stuff with there. And I think you might be able to prove through that you'll never take the maximum one, but I won't say for certain yes or no. Unfortunately, we won't cover that one today. Maybe we'll shove it in next week. Okay, before we get into the many different approaches to solving this question, what did we try with Germany? Let me clarify the question. In the Germany example you had, what did you guys, the students, attempt? Like, what was your thought process in solving it, or just trying your best? Yeah.
I think the most intuitive thing was like where you see a cluster of things like very close to each other, you like start it out there because then you just have to like just follow that. Like you don't have another option.
Yeah, I think there were like 4 cities that were like right there,
Yeah.
and if
So I just
there's
have to travel.
like you're more than likely going to want to do something like
Yeah.
that instead of like here.
Yeah.
Okay, makes sense. That's pretty logical. Other strategies or ideas? Yep.
I think, like, in general, as a, like, of course, apart from these very basic strategies, I was trying to stick to the boundary as much as possible. So, like, that prevents, like, zigzagging. So I didn't want to come, like, inwards if there was an outside edge that I could go more to, and I think that worked out well.
Yeah. We won't talk about this today or maybe even next week, but that's a very similar strategy to what I had, where essentially the idea is you have a set of points and you can construct something called a convex hull, which I won't describe what it is, but it's just how can we enclose the points with the least amount of space. So there is an approach which you compute a convex hull and then you sort of traverse these edges and try to like build inward. So that solution does exist. It's just quite complicated. If I remember correctly, I think the runtime is like that for a convex hull, and then the worst case solution is actually like not good at all. Like in the absolute worst case, it doesn't compute it very well correctly. I don't think there's a quantification for that.
It doesn't compute it correctly.
Hmm?
Did you just, like, does it like not
It
work?
must be, like, exponential time.
No. I think the convex hull always takes n squared log n. The additional steps that you do, I think that also runs in polynomial time. It's just that it won't get you an exact solution.
If it did, that would be...
Then it would be in P, right?
Okay.
Yeah, so since it's like a bit away, you can find a worst case where a bit away becomes a large amount away. I didn't read too much up on that, but I think that's that. But yes, this strategy kind of exists and works. Other ideas? Okay, I'm surprised no one said the most obvious strategy, which is to solve it with constrained programming. So it's slightly disappointing. Obviously, I'm joking. So yeah, we'll take just a couple of minutes to talk about constrained programming before we talk about other things. So if we were to formulate this as a constrained program, how would we do that? Variables, their values, constraints, etc. What would we say?
I think like my first guess is that we have indicator variables for each of the edges, which is 1 if that's included in the tour and 0 otherwise, and then that our constraint would be that like, and then we might even need like indicators for the vertices that show if a vertex is there, like is being covered by one of the edges or not, and then the constraint would be that all of the vertices should be, like the indicators for them should be 1. And then from the indicators we can also calculate the edge weights easily, because if an indicator is 1, then we add the weight to the weight of our tour.
Excellent. Yeah. So exactly, our variables will be exactly that: indicators for each edge if it's included in our tour or not. The constraint is that each vertex has to be visited exactly once. is there a way, maybe just for an arbitrary vertex v, with respect to all of our variables, can we form some sort of linear constraint that expresses it?
We know how to do exactly one constraints. So
Mhm.
we can make an exactly one constraint for like all of the variables that are, so all of x, v, comma, u for all u's that are not equal to v, all vertices that are not equal to v,
Mhm.
exactly one of them is 1. And, I mean, yeah, just that suffices.
Yep. Whatever, v comma u. An equivalent formulation is we can use a summation, and it's pretty much the same thing. Sum over all other vertices, look at their indicator. If it's 1, that means that edge is included in our tour. If it's 0, it's not. So if the summation is exactly 1, that means exactly one indicator is 1 with starting point v, which means we're leaving the vertex exactly once. And then the other way around means we're entering it exactly once. Yeah.
Does this create like 2 separate loops? That
Yes, and you spoiled my parade, but excellent observation, Chris. So the cost is exactly like that. I'll just skim over it. Do you have a question?
You don't need to justify, put that second constraint in, right? Like the sum of x, j, i.
Well, I guess that means you need to enter it exactly
Yeah, but if you
once.
just have your constraint saying that there's exactly one edge leaving every vertex,
Mhm.
because you're checking for all vertices, overall you end up checking the second one once you check all vertices, right?
I think so. I'll have to
Wait,
check.
But if you have two vertices which satisfy the first condition that they all have like one exit,
Mhm.
what if they exit but enter the
same point?
Yeah, same point.
They
Yeah.
won't be able to because you are ensuring this happens for all. You can't come up with a case where it happens for, like, this constraint is satisfied for all of the n and you still have that case.
So I think that there's one that's entering also will be 2.
Does that
Yeah.
match what you're saying, Thomas?
Yeah.
So each one of these exits, there's one edge that exits it.
But that one has 1.
That one also has one edge that exits it, but not all of them have one that enter it. Good, so we do need that. Chris, can you repeat the question you just asked me a minute ago?
what do you do to prevent there from being multiple loops?
Why would there be multiple currently?
If you use that example, you could have like, or if you use four vertices, you could just have 2, each pair like goes to each other.
Excellent. So this is just a great observation by Chris, in that like in the current formulation, just by saying we enter each vertex once and exit each vertex once, doesn't guarantee that we have a single cycle at the end. So for a better visual example, here we have K5, and so ideally we get something that looks like this from our output, a single tour that visits all the vertices, but in the current formulation, we could get something that looks like this, 2 separate sub-tours, and they themselves are cycles, and they would match all of the constraints that we've given thus far. And so I will turn the question to you. I won't answer it. How do we fix it? Yeah.
This could be wrong, but like if we know that, like for example, the right subtour example, we know that x23 is 1 when you create the edge from 2 to 3 in your tour.
Mhm.
Then you force x32 to be 0, because then if you have both 2, 3, and 3, 2, they become an independent cycle.
Good. So that would force us to not have cycles of size 2.
Yeah.
This is a small example, so like cycles of size 2, but like if you imagine 100 vertices, is it possible to generalize that for more vertices?
Oh,
Mhm.
if at any point we have like some like if like for one vertex we have both an outgoing and an incoming edge into it, then we know that this cycle is complete. So if we have like x2i and then some other thing into 2 and both of those indicators are 1, that means something is leaving 2 and something is also entering 2. So that means our cycle is complete, and we only want that when our overall constraint is satisfied.
Right. So how do we implement that?
So like all the vertices, unless they're like covered, unless like they have some edge that is 1, until then we can't have something entering and something leaving. So
Good. I think we're getting there. let's do a throwback to CIS 1600, my favorite class.
Hamiltonian cycle.
If Junior, you have an idea?
Well, actually, I don't think it's the idea that you would say, but like, is there a way we could add atmosphere constraints to like, say all of those are reachable to each other?
That's an interesting idea. So basically saying like a single strongly connected component? Maybe. The question is, how do you encode the reachable constraint? Because right now our variables are just, this edge is 1. And since you're dealing with a complete graph, reachability can grow like really, really large. Like if I consider, 1 and 4, there's a lot of different paths.
Yeah.
So good idea. Thomas, you have an idea?
Is it possible to like number the vertices as you go, such that the nth vertex points to the first vertex? Is that possible?
I'm not too sure because like here currently, if I just change these names to 5 being 4 and 4 being 5, then that would satisfy your constraint of 5 pointing to 1.
No,
but we don't have it.
You don't have them numbered initially. You number them as you go. So until like you detect that okay, I'm on my nth vertex and I should point to 1. If I'm not pointing to 1, then it doesn't work.
Maybe. My only concern about that is that like in this constrained programming world, we're not really building the Tor iteratively. It's sort of like, here are my variables, Mr. or Mrs. Solver. You set numbers equal to each other, and then it will just return to me something. Okay, so I'll give a hint. We'll think back to CIS 160, and the question is, if I have n vertices, what is the minimum amount of edges I need amongst those n vertices to have a cycle along all the vertices? N. So, if I have these 3 vertices, what I really want is for there not to be 3 edges that traverse those 3 vertices in my final path. Right? That is simply the observation. We don't want a cycle, so our solver shouldn't return anything where we have 3 edges amongst those vertices. And so a possible idea, you can ignore the last bullet point for now, even though I just drew your attention to it, says that consider every single possible subtor of vertices and make sure we take less than S edges between them. Because that'll guarantee that we won't have a cycle. S or more, we'll have a cycle. And so, it's as simple as that. For every single subset of the vertices, go through every pair of vertices in that subset, sum up the indicators, and we want to make sure that the amount of indicators that are 1, the amount of edges in our Tor, is less than the amount of vertices. And now I really should have blocked this off, but I forgot to. And the main issue with this is that there's a lot of different subtors. So there are ways to fix this by like adding constraints lazily, similar to what we talked about last week. I won't go into that. As a general note, it turns out constraint programming is not quite state-of-the-art for TSP. So, yeah.
Yeah, if we could add an exponential number of like constraints, then there's like so many simple things that you could do for this, right?
Yeah.
So I'm not understanding like the ways to fix that part. Like, what does it mean to add constraints lazily?
So how it actually works for this is a bit beyond my knowledge. But I think the approach is kind of similar to what we briefly talked about last week, where we were kind of creating a SAT formula, and we said that okay, if I take this constraint and I write it as a bunch of clauses, I'm going to be adding a whole bunch of clauses. So we took inspiration from CDCL to add clauses as we go. So it's a similar idea that motivates that, where we'll be able to add constraints kind of as we go. I can also give you a reading on that if that's interesting, but Point is, unfortunately, constraint programming doesn't work too well for this problem. So instead, what we'll turn to is heuristics. So TSP is what we call an approximation-friendly problem, which means that a good enough solution is usually good enough, right? If I wanted to visit those 25 cities in Germany, which I don't plan on ever doing, if the best distance is 3,050 kilometers or whatever it was, and instead we use Tunier's solution of 3,100 kilometers, I'm not going to throw a fit because it doesn't really matter too much to me. So in practice, if you have a solution that's good enough, that usually serves our purposes. So we're going to explore a bunch of different heuristics that are pretty similar to one another that will help build up to a solution that's good enough. And these are very, very simple heuristics, very simple tools that you can use. And they'll end up getting us pretty decent solutions. Okay, my iPad's going to run out of battery. And that just means we're going to wing it. So here we go. That's not a good sign. Okay, so the first heuristic we'll talk about is called nearest neighbor. And for the machine learning inclined people, this has nothing to do with that, nearest neighbor. It's pretty much exactly what it sounds like. So the heuristic is like this. Actually, I won't call this one the heuristic. We'll just call this a procedure. We'll choose a starting vertex, call it U, and then from that vertex U, we'll look at all of the other unseen vertices. And all of those vertices are adjacent to U because we have a complete graph. So I can go from U to any vertex. So I'll look at the one that is closest to U, and I will travel there. And then I'll continue doing that. So I'm at a new starting point. I'll look at all of the remaining vertices, pick the one that's closest to me, go there, and so on and so forth. So this is a greedy approach where we're just greedy on distance. We just keep on asking for the shortest distance. And the nice thing, it's very simple, it's intuitive, and it's pretty efficient. So let's see how it works. We have the graph that we started with, and we'll just say we're starting at vertex 1, and we'll see what happens. So step 1 is to figure out of all of the remaining unseen vertices, which one is closest to me. In this case, it's 4. So I will simply travel there. 1 to 4. I have 2 more vertices, so I will choose the closest vertex from where I am. So currently I'm at 4 because I just traveled there. So next I would travel to 2 because it's 10 versus 15. So I'll go to 2. And then I'm at vertex 2. I choose the one that's closest to me out of the ones that are unseen. This is the only unseen vertex. So I'll travel along this edge. I reach 3, and then I have to return home. So in total, the cost is 95. And the optimal cost we saw in the previous slide was 80. So not too great, but okay.
Wait, how do you know where to start?
You can just choose it arbitrarily. It shouldn't matter too much because you might get different paths depending on where you start. But since it's cyclic in nature, I could have started elsewhere. Like I could obtain the same path by starting elsewhere. It's not too bad. But for now, we can just assume it's chosen randomly.
That's what I was saying, because if it's the nearest neighbor procedure is of course linear, right?
Mm-hmm.
In time. So if we can just do it, or it's polynomial in time at least, we should just do it from all of the vertices and take the one that gives us the short distance. Because if you start at 2, you do get the optimal one.
Yeah, if you start at 2, you get, and I think if you start at 3, you get something different, right? You go to up here,
3 gives
and
you
then
optimal as well.
there, and there, and then there.
Both 2 and 3 give you optimal.
Yeah. So
Even 4.
in this case, it gets you optimal. Not always.
Yeah.
So, okay, that is the first heuristic, and we'll just keep it in mind. I won't comment too much on how good it is or how bad it is. We'll see that kind of at the end. But we'll just keep this heuristic in mind, and when we refer to NN, we'll talk. This is the idea. So questions on this procedure? It's pretty simple, pretty intuitive, not too bad. So here's another idea. This is called nearest insertion. So the idea of this is let's stay greedy, but let's be a little bit more smart about how we do things. So the idea is we'll start at a vertex, and then we'll look at all of the unseen neighbors for any of the vertices in the tour. So, for example, that's a bad example. So in this example here, when we were doing nearest neighbor, we were at vertex 2. We looked at the nearest unseen vertex from vertex 2, and it was 3. So we took this edge here. Now we're going to say that, okay, we'll look at all of the vertices that we've seen, not just the one that we might be at, and find the nearest neighbor. So maybe in this case, it would be this edge connecting 4 and 3. So that's the first critical difference. So we'll find the nearest unseen out neighbor of any of the vertices in the tour. And now we'll insert that vertex somewhere in the middle of our tour. So with nearest neighbors, we were always adding a vertex to the end of our tour. We were traveling there and adding a new vertex. Now we're going to take the opportunity to insert somewhere in the middle of our tour. And the way we'll do that is by looking at this expression right here. And it's a little bit ugly in terms of math, but it's very easy in terms of intuition. The idea is, suppose we're on our tour. We have some sort of partially connected tour, and we're following this procedure where we find the nearest out neighbor that's unseen. So maybe it's this vertex X. And the nearest part comes from perhaps this edge. Let's just say it has weight W1. So we're inserting it in such a way that we want to travel from this vertex to X and then back to where we were going to reach, and we're just going to remove this edge. So the operation of an insertion is add 2 edges and remove the edge that was already existing. It is simply inserting a vertex. So we're going to insert it into the place. We'll check between every single pair of vertices where we minimize the total amount added, and then we'll keep on doing that. And we'll see the visual in just a moment.
I'm a bit confused. So can this also pull out vertices that are already there on the tour?
No, so everything that is already existed on our partial tour will remain. So before I had I and J on the tour, and then I'll find some vertex,
Not on the tour.
and maybe it is optimized to insert it in between I and J, and so I will insert it in between I and J, and I and J are still on the tour, they're just not next to each other.
No, but can that the third vertex that we inserted into the tour, I can't pull out from
No,
vertices
no.
before
We're only looking at things not yet on the tour.
So how does the tour get created?
We'll see. We'll see the visual.
It's not necessary for the insertion, based on the optimization that we have there, it's not necessary for you to choose the closest vertex on the current tour to the new vertex, right? Because you're optimizing
Correct.
for the sum of the distance from that vertex to adjacent one. So hypothetically, if I was the closest, this was X,
Mhm.
but both the ones adjacent to I were really far,
Yes.
and then you had 2 that were more far away from I, but they were both relatively close to X, so it's better to insert it at that point.
Yeah, so the vertex that we're going to look at to insert will be the nearest unseen out neighbor, but where we insert it may not be at the point where it's
But
nearest
that's
to an
only 2
existing
options,
vertex.
right? Either right ahead of it or right behind it. Because
Not necessarily.
the way it's written there, it's saying you're subtracting W of Ti, comma Ti plus 1.
Mhm.
So they're adjacent vertices.
Yeah, but we're going over every single vertex in our tour.
Correct.
So, we have a tour.
I think what he's
And then
asking
extra
is-
vertex there. And we're going to see, can I insert it this way, this way, this way, or that way? We'll check all of those. Check all the sums. That summation right there. Let's do the walkthrough, and then maybe it'll be a bit more clear. So we'll start at vertex 1. Again, I guess just chosen randomly. And then we'll look at the nearest unseen out neighbor. of the entire tour. So in that case, it should be 4 because it's 20 away. So next vertex is 4. And then we would do the summation checking, but since there's only one vertex, we'll just ignore it. So we'll just say, let's travel to 4. The next vertex is where things get interesting. So now we would, again, check what is the nearest unseen out neighbor of any of our vertices. So 1, it's neighbors that are unseen. It's 2, weight 25. This is weight 30. Here, weight 15, weight 10. So 10 is the least amount. So 2 is the vertex we'll focus on next. And then we're going to say, where can we insert 2 into our tour? If we're starting at 1, our options are either we immediately insert 2 in between 1 and 4, that is, we go from 1 to 2 to 4, or we insert 2 at the end, go from 1 to 4 to 2. We're just considering where could we visit 2 in our partially created tour. And to determine where we would, we'll check what is the net change in cost, or like how much cost are we adding to our solution when we do that. So if I insert after 1, then to construct my tour, I would have to add in this edge from 1 to 2, add in the edge from 2 to 4, but I would remove the edge that I've taken from 1 to 4. So that's this summation right here. Weight of 1 to 2 plus weight of 2 to 4 minus that 1 to 4, because we're removing that edge. And that has some weight 15. The other option is insert after 4. So here, I'll explain in just a minute. But we would check, okay, 4 to 2 plus 2 to 1 minus 1 to 4. So this might be a little bit confusing, but the partial tour we're creating, you can imagine it as like a closed cycle. So this means that we're going from 1 to 4 to 1, and we're just building up on top of that. So if we were to insert after 4, it would be 1 to 4 to 2 to 1. So in order to see the net change in cost, it would be, well, instead of going from 4 to 1, I'm adding this edge, adding that edge, and then removing the edge back. Chris?
Can you add, instead of like in between them, can you just add them to the end?
So added to the end?
So like instead of 1 to 2 to 4, can you just go like 1 to 4 to 2?
1 to 4 to 2 to 1. So that is this case right here, inserting 2 after 4. Okay, so if you imagine like the written tour is the partial tour. This is the disclaimer I gave early on, that tour might be used in the wrong sense. The partial tour that we've built up so far is 1 to 4 to 1. Eventually, we want to encompass all of the vertices.
Yes.
Choose the next choice. Where do we put it? 2 options.
So it's not like linear like it is there. It's like 4. Or like in the example you gave earlier, where it's like 5 vertices and 4 edges. It's like that, and then there's also an edge back to the first one, right?
Yeah. So like 1 and 4 are in here,
gotcha.
2 up there.
Yeah.
I think you got it. Other questions right here. Okay, so in this case, these net changes in weight are the same, so we would just choose one of them. Here we just decided to add it after 2. So, or after 1. The dotted line is representing like us traveling back. We're just expanding on it. So that's that. Okay, so then we would continue the procedure. Look at the nearest unseen vertex of any of the vertices in our tour. In this case, it's kind of boring because there's only one unseen vertex. So that would be that. And now we have 3 possible places we could insert it. Either after 1, so that would be the path 1, 3, 2, 4, 1. We could insert it after 2, meaning we go 1, 2, 3, 4, 1. Or after 4. 1, 2, 4, 3, 1. That's stupid. And in doing so, in each of those options, it's the same exact idea, that we're going to be removing an edge. So for example, if we insert it after 3, after 1, that means we never are going to travel along this edge 1 to 2. We will remove that edge and instead go 1 to 3, 3 to 2. So what would be the net change in weight under that particular example there? Like when I show the summation, what should that? What's it?
40.
40, so it's 30 plus 35 minus 25. Exactly. So yeah, the first one is exactly what we just discussed. 30 plus 35 minus the 25 we removed. And then you do that for the other options. And in this case, the best choice is to insert it after 4. Now we visited all the vertices, so that would complete the tour. In this case, we happen to get the optimal solution. Yeah.
Why are we choosing the, like, I know in this case it didn't matter, but why are we choosing the next vertex to check by finding the minimum edge? Like you chose 3 because there's like an edge from 4 to 3 of weight 15. But then what actually matters is not just the smallest edge weight, it's that sum minus that difference. So shouldn't we be calculating that sum minus that difference from all possible, like all vertices on the current tour to all remaining vertices and then choosing based on that?
You could. So that's the thing about these heuristics.
Don't
You can
perform better.
It might. So we'll talk about performance at the very end. And the thing is, like, it's slightly difficult to quantify performance. Like, I could just tell you that, oh, maybe nearest insertion is better than nearest neighbors, but it's not really easy to say why. So we'll see a little diagram at the end. But the point I'll say is that, like, heuristics, you can kind of do whatever you want. This is one of 2 more heuristics we'll see. So it's just going to be different approaches. And again, we're just looking for an approximate solution. So yeah, you can add on to the heuristic. That might get something better. They can be lightweight, like this one is, sort of up to you. I know, like, this vagueness or abstractness is a little bit uncomfortable, but sometimes we just have to sit content in the discomfort and be like, okay, this is a tool, and it kind of works. Like, it gives us a pretty good solution here.
Is there like intuition on a case where this wouldn't give the optimal solution?
I don't have that intuition.
That's fine. I just couldn't think of things.
Here's an interesting idea though. Like, let's take Ishaan's idea of, like, you know, why are we choosing the nearest unseen out neighbor? And let's take Chris's question of, like, why is this so unintuitive? And kind of combine those two in the wrong direction. Farthest insertion. Same thing as nearest insertion, except now we will choose the farthest unseen out neighbor.
Is there also a random insertion?
There is a random insertion. We're not talking about it today, but there is random insertion. Now, that's the only change. We're looking at all of the unseen out neighbors, and we're choosing the farthest one, and doing the exact same thing, computing the insertion cost, the net change in weight, and keep on doing that, adding it to the tour. When I first read this, I'm like, how in the world does this make any sense whatsoever? And so this intuition here is kind of poor. The intuition I'll give to you is that when we dealt with the greedy sense, the nearest neighbor sense, and kind of with nearest insertion, we were very early on greedy with the weights, meaning starting out, we always wanted to get the closest neighbor. But as you do that, it may compound into a bunch of bad decisions where at the end, you're dealing with a lot of very heavy edge weights. So I think if we go back to here, we started out quite nice, but then the last decision we made just happened to be a very, very bad situation where we had to choose this 35. And that's kind of a consequence of us being very greedy early on. So for this insertion, the idea is, like, maybe let us go the other way around. Maybe let's make some bad decisions early on, potentially, using the farthest unseen out neighbor as a starting point. And then maybe later on down the road, we'll have some good situations later on. So it's kind of like a reverse greedy in a sense. Again, makes no sense whatsoever. But let's see how it performs. Walkthrough. Start at vertex 1. We would choose the furthest unseen out neighbor. So I believe it should be 3 in this case. Yes. And then we would insert it. There's only one place to insert it, right after 1. So that's our partial tour. What vertex should we visit next? 2?
Yeah, 35.
35. Yeah, I don't see anything larger than that. So 2 would be our next candidate vertex. And we would check the insertion cost. What happens if I insert it after 1? Well, in doing so, I have to add the edge 1 to 2, I have to add the edge 2 to 3, and I have to remove the edge 1 to 3. That gives me a net change in weight of 30. And after 3, do a similar calculation, weight 30.
Shouldn't the way we define furthest be not the maximum edge weight, but the vertex that has the maximum, vertex that has the highest minimum distance to the current cycle?
No, not for this heuristic. We're just saying the furthest one away
From any of the vertices.
from any vertex in your tour that you've seen already.
Then that intuition about building the outline doesn't make sense.
Right, which is why I said to kind of ignore that point. But okay, here we're tied, so we would just choose somewhere, I think, yeah, insert it after 1 here. And then we would check the next vertex, since this is only 4 vertices, there's only 1 more. And again, compute all of the net changes in weight. Interestingly here, after 2, we get a decrease in the current cost, which is a consequence of us choosing the heavy weights early on. So, we would insert after 2, and we get this tour right here, which also happens to be optimal. So the only point I want to make with this is that the procedure seems very unintuitive, and it is. And yes, this is a small example, but somehow, in this case, it ended up getting optimal. And I guess if you try it at a different starting point, you'll get something kind of close to it. But again, it's a small example. And we'll see the comparison at the end, trust me. Questions on farthest insertion? I know, it just doesn't sit well, like any of this. It's just like, here's an idea, we've run it, so what? And I wish I could say that there's a great culmination to this lecture, but there really isn't, so I don't want to get your hopes up. So, yeah, like, these heuristics as a whole, it's just like, the naive approach with nearest neighbors is good. It's like the first thing you think of, but it doesn't work too well, kind of for obvious reasons. So these heuristics are just a little bit an extra step that we can make our procedure a little bit better. We can insert in the middle of our tour. And they're a little bit more expensive than nearest neighbors, but so what? They give us a little bit better solutions. So here's a little bit of a teaser. That interestingly, the furthest insertion one works well in practice, but nearest insertion, not so much. And what's the intuition for that? No bloody idea. So, sorry. That's why I said there's no good culmination. One more heuristic. This is called the Savings Heuristic. This one's a little bit annoying. So here, we'll choose a single vertex to be the central vertex, and we're going to start with a bunch of subtours. These are going to be very small loops from that central vertex to all other vertices. So if I have 4 vertices, and you can imagine edges between all of them, and let's just call X my central vertex, I'm going to start with a bunch of tours that go from X to one of its neighbors and back, and same thing for all other neighbors. That's just the starting point. Now, we're going to compute something called the savings for each edge, which is, I guess, with respect to the central vertex, what happens if instead of, I guess, taking the edge from, let's say, I to J in my tour, like if I chose to do that, what if instead I go from I to X and then X to J? It's very similar to the insertion stuff we were doing, it's just with these random edges. So we're going to compute something called savings for each one of them. And then we're going to sort them in decreasing order. And then we'll process those edges in decreasing order. And we will add the edge if certain edges are already in our subtours, meaning I to X and X to J are in our subtours, and they're not already in the same tour. Bloody confusing. Let's see an example. So This is the exact diagram that I just drew. So we'll choose 1 to be our central vertex. And we have a bunch of these subtours. Everything highlighted in red are our subtours. Then we're going to compute the savings. So for each edge between the other vertices, so for 2 to 3, for example, we'll consider what happens if we instead go from 2 to 1, 1 to 3, and exclude the edge from 2 to 3, just extending our path. So, do the same calculation we've been doing. That gets us something called savings. So in this case, the edge 2 to 3 has savings 20. Do it for the next edge, 3 to 2. Same idea. Go from 3 to 1, 1 to 2, get rid of 3 to 2. That gives us savings 20. Do it for all of these edges. We have a bunch of savings values. Now we're going to process them in decreasing order. So we'll start with 4 to 3. That's not good. Whoops. Okay, and then the question is, where are my notes? Please have battery. Yes, 2%. Let's go. Okay, so the question we ask when processing a vertex, or an edge 4 to 3, is, are the edges 4 to 1 and 1 to 3 in our subtours? In this case, yes. Like we have 3 subtours, but both of those edges exist in some subtor. And then the second question is, are they in different, are the vertices in different subtours? And in this case, the answer is also yes. Separate subtours. So if both of those answers are yes, then we will include this edge 4 to 3 and remove the edges from 4 to 1 and 1 to 3. And this seems very, very complex, and it kind of is, but it's almost going backwards from our insertion sort. Instead of inserting 1 in between 4 and 3, we're starting out with 1 inserted between 4 and 3, and now we will break that vertex away. And now we'll just say, we'll include 4 to 3 based off of our procedure. So then we would check the next edge, 3 to 4. And the question would be, are the edges 3 to 1 and 1 to 4 in our subtours? And in this case, the answer is no. Or, no, the answer is yes, both of these are there. But then the secondary question of, are those vertices in different subtours? The answer to that is no. So we would skip over this edge. Move on to the next one, 4 to 2. We would ask, are 4 to 1 and 1 to 2 in our subtours? In this case, no, because 4 to 1 is not in our subtor. So we would skip over that. Look at 2 to 4. 2 to 1 and 1 to 4, both in our subtours. And both vertices 2 and 4 are in separate subtours. So we would add that edge in. We're sort of uninserting the 1. And we keep on doing that process until we have 1 tor remaining. In this case, we have a single tor. And that gives us weight 80, which happens to be optimal. But again, it's a small example. So again, not very intuitive, but it's almost in a sense the opposite of the insertion, where we're removing 1 inserted in between everywhere. We're just sort of pulling it out. Again, I won't make many further comments. It's just another approach to solving it. All right, so when I asked you guys, how did you solve Germany? Again, how did you solve the Germany TSP problem? You could have said, I used the savings heuristic. I would have called you crazy, but it is just another approach that works great, and it might work well. Questions on the savings heuristic? Okay, so here is the ultimate comparison. You can take your time to sort of parse the graph on the left. I didn't really care too much about the axes. I more so care for what the arrows are indicating. So these algorithms have been extensively tested on a bunch of different data sets. And this is sort of a visual of how they compare with one another. So, it turns out that nearest insertion is kind of the worst one. It has a worse solution and worse runtime. Worse runtime means it takes longer. Worse solution means that since we're not getting the optimal solution, we're getting an approximate solution this is saying that our solutions tend to be further away from the optimal value. So yeah, nearest insertion is the worst. Nearest neighbor, also not a great solution, but it has pretty good runtime, and that should make sense because it's just greedy. And then you have these down here, where furthest insertion and savings, the two very, very confusing ones, happen to work better, with furthest insertion working a little bit worse in terms of runtime. So in practice, it turns out that the savings idea is the best. Why? I'm not sure. And again, there's so many different approaches you can take. All of these, convex hull, all of the other ideas we discussed. In practice, what works well? I guess savings works pretty well.
In this, something being on the x-axis means that it's like perfectly optimal, like it gives like the true correct answer. Or is there like some margin of error even on the zero?
So I guess like the y-axis, you can think of that as like how close to the solution it is. So like the further up you go on the y-axis is like you're further away.
And the zero means like it's exactly the same as the optimal solution.
For the sake of visual, yeah, you can assume that, or it's like extremely close to it. Yeah.
What is the greedy solution? Is that different from NN?
That's a good question. Yeah, I'm not too sure why that's there. I'll have to look into that. Yeah, I don't know. Okay, let me just see if I can show something. So on the train ride here, I was like, let me ask ChatGPT to code up all of these heuristics, and we can run them quickly. So ChatGPT was great in doing that for me. So here we have 20 U.S. cities, and this is the beautiful matrix that shows the distances between each pair of cities. And I believe it coded up most of these correctly, except for savings, which doesn't work, and I didn't have time to fix it. So let's just see what happens when we run these. So
It was all this code just working like right out of the gate?
No, I was debugging on the train. So nearest neighbor starts in Austin and takes this wonderful path. And I'm not too good with my Texas geography, but something about this doesn't feel right. Like, I would think Houston is closer to Austin than San Antonio. Is anyone from Texas here? No? All right, so I just don't know. All right, maybe they just really wanted to see Wemby play basketball. Anyone a basketball fan? He dropped 50 last night. Do you see that?
Who did?
Wemby.
Wemby, is it?
Yeah.
Oh my
He
god.
dropped 50 on like really good efficiency. But Giannis got 59. Dropped 50. Unbelievable. Anyways, this path is 10,000 miles. Nearest insertion, New York to Philadelphia. That's what I did today. 8,802 miles. A drastic improvement. And furthest insertion, a little bit better. So it kind of matches the graph that we saw before, where furthest insertion was one of the better solutions. And I'm sure if ChatGPT coded up savings correctly, it would be good as well. But for a bit more tangible example, something closer to home, we see kind of matches. So hopefully that's interesting. Okay. I won't spend too much time on this. But it's just interesting to note because this is a very popular problem as well. So the vehicle routing problem is essentially a derivative of TSP, the Traveling Salesperson Problem. The setting is exactly the same, where you have this weighted complete graph. But now instead of like a single person traveling along all the vertices, maybe you have a fleet of vehicles who need to together travel to all of the vertices. So the individual vehicle doesn't have to visit all of them, just together they have to visit all of them. And this kind of makes sense. If you're Amazon, you don't want a single truck going to all of the cities in America. You want to send out your fleet to visit a bunch of different homes. It's an important problem. And again, the goal, find your routes that minimize the total distance traveled or the total minimum weight. And extra constraints exist. These are further variations of the question, which I won't even talk about, but like, maybe there are constraints on your vehicle, how far it can travel. Maybe the trucks can't go very far. Or maybe the trucks can't carry that much within them, and there's that extra carrying capacity. So again, all of these questions, hopefully you can see, like, they are important in practice. Amazon probably has to solve these. And so it turns out that the savings heuristic was built as a solution to the vehicle routing problem. And we can just take the algorithm that we came up with and just change some very subtle things. The main thing is right here is just that, like, if we have additional constraints on what goes on, we just need to check if adding in an edge violates our constraints. But in general, ignoring the red stuff, the savings heuristic is a pretty good approach for the vehicle routing problem. And again, I didn't want to talk about this too much. OR Tools has a very good suite of TSP-related stuff. So they'll solve the vehicle routing problem. They'll take care of all those extra constraints. This link is really, really great. There's a lot of really good information on there. I was just scrolling through it and looking at the nice pictures. So I encourage you to look at that in your free time. These are just some hacks that you can do if your edges are of a certain kind, but that's not super interesting. And then here's one more comparison. So if we use the TSP solver from OR Tools, obviously it's not always going to produce the optimal solution because that's kind of hard to do. So how does OR Tools TSP solver work in practice? You can take a look at this chart here. So this is run on a bunch of different, I guess, like countries or territories, those being listed here. Each one has a certain amount of cities, and it was just solving the TSP problem on those cities. And so you can see the comparison that, like, okay, I guess for Western Sahara, yeah, it's pretty close, but makes sense. It's a small amount of cities. Pretty low percent error. But as you increase to more cities, close to 2,000 cities, you're getting 6% error. So 2,000 cities might be a lot, might not be too much, but we're seeing that we're increasing in error. So OR Tools, not that great, I guess. I mean, it's pretty good. Like, that's why it exists. But you can see that, again, we're just approximating it, and we're just saying good enough is good enough. In this case, traveling 92,000 kilometers versus, or I don't know if it's kilometers, but 92,000 whatever units versus 86,000 whatever units, most likely I'm not going to throw a fit.
Where did they get the optimal cost?
I think it was probably already known, like, as a given. I don't think it was computed, but maybe it was run on some other machine that solves it optimally. I don't know. Good question. You guys have a lot of good questions that I unfortunately don't know any of the answers to. That's it. So, yeah, pretty unsatisfying, a lot of this stuff, and how some of those heuristics that made no sense ended up working the best. But we'll hold on to it, and I think next week we'll talk about a couple more heuristics. I'll try to see if we can shove in a couple of these, and wrap up. And then, I don't know, I'll ask you guys what you're interested in hearing about for the last lecture. I have some ideas, but we'll choose something that most people are interested in. Cool. If nothing else, you're free to go. Don't forget about your projects, and next week class will also probably start like 5-10 minutes late, but be here on time, and maybe I'll give you an exercise.